Hey guys, Tarek Face here. I have tried to record this so many times. I hope this is the one. It will not be under 5 minutes. I apologize. But anyways, cold temperature corrections. Why we need to do them and how to do them. So why do we need to do them? First of all, air and how it changes with temperature. So the hotter the air is, the more energy air molecules have. And if they carry more energy, they can force each other to be further apart from each other. Whereas when air is colder, they have less energy, so they tend to bunch up together a little bit more. So as a result, cold air is denser. Denser being there's more air molecules in a given space, and hot air is less dense. And so if we look at a sort of a mental model that I like to use, um, pressure is a gradient, right? It doesn't work in layers. It's a a non-linear continuous thing. But I like to use this as a mental image to help understand pressure as it goes up in the atmosphere. So if we're to imagine each layer represents a certain amount of pressure, that layer is going to be thinner in cold air than it is in hot air because it's denser. So the gradient is going to be steeper. And so if we look at how that would apply to us as pilots, so we're flying, it's the correct pressure, the exact same pressure, exact same indicated altitude. The altimeter is working fine. It's the same altimeter, same airplane. And the only difference here is that the temperature is different. In the hot air, the actual height will be higher, will be greater than in cold air, right? And so because of what we said before, and that's great and all, right? But how much does it change by, right? Because we're showing diagrams, it's not to scale. What's the actual physical difference? And well, there's a rule of thumb, and in words, it's 4% of the true height. Note the word height for every 10 degrees Celsius from ISA, International Standard Atmosphere. And so, again, great, but how do we calculate this? And so there's a formula for you. Here it is. That's that sentence in a formula. Altitude correction is equals to 4 times the height divided by 1,000 times the ISA deviation. Now, that's the second time I mentioned ISA. If you don't know what ISA is, it's a model of the atmosphere. It's basically like a standard model of the atmosphere. We can make a video about it, but for temperature, it's 15 degrees at sea level, and it reduces by 1.98 degrees Celsius every 1,000 feet. We can round that up to 2 degrees per 1,000 feet. Okay, so let's look at an example. If we're flying at 3,000 feet, we've got the correct hectopascal set in, the correct pressure set in, and the outside air temperature is minus 10 degrees Celsius. What is our actual altitude, right? We've got indicated 3,000, but what is the real altitude? Well, first we need to calculate the ISA temperature. So at 3,000 feet, what would the ISA temperature be? Well, at sea level it's 15, and remember it's 2 degrees for every 1,000 feet that we reduce by. So 3,000 feet, 3 times 2 is 6. So we remove 6 from 15 and we get 9 degrees Celsius. So in the ISA global model, we would expect the temperature at 3,000 feet, oh, I'm going too far ahead, to be 9 degrees Celsius. But the reality is different. The reality is that the OAT in this scenario is 10 degrees or negative 10 degrees Celsius. So ISA deviation is the difference between those two numbers. It's the difference between ISA 9 and the difference and OAT 10. So we do minus 10 minus 9 because we're getting a difference, and we get minus 19. So the ISA deviation is minus 19. So now we can apply those numbers to the altitude correction. So if we first, and of course, sorry, one more thing, we're also going to assume that we're flying at 3,000 feet altitude, but it also happens to be our height. So there's no mountainous terrain or hills. We're flying over, say, the beach, for example, or over the coast. So if we plug those numbers in, first we plug in the height, which is 3,000. So 4 times 3 divided by 1,000, which is 4 times 3. And then we multiply that by the ISA deviation, which is minus 19, and that gives us negative 228. So we need to add that to 3,000 feet to get the correct altitude altitude. So the real altitude. So our actual altitude would be 3,000 feet plus minus 228, right? So that gives us a smaller number of 2772. So our altitude might be indicated as 3,000 feet, but our true altitude is over 200 feet less at 2,772 feet. And that's great. In reality, when it comes to the practice of knowing this, we tend to do the reverse. We tend to change um, indicated to we change actual to indicated so that we know what indicated altitudes we fly in order to get an actual altitude that we want. We're gonna see an example in a second, but first off, when do we apply these corrections? And so, according to Panops, the rules are when the sea temperature is below 0 degrees Celsius. And we apply it to all the altitudes indicated in the instrument approach procedure. There's an asterisk, we'll talk about that in a second. And to the DA and MDA, so the decision altitude or the minimum descent altitude. And legally, technically, we only need to apply it to the instrument approach procedure altitudes if there's high terrain in the vicinity, sort of over 3,000 feet above mean sea level. We're good pilots, we're going to do it all the time. And by the way, this is oversimplification. There are caveats to that rule, which is why, as good pilots, we'll do it all the time. Okay, so here's the real world example. I like this airport. This is Ohrid, which is in Macedonia. And it's a really cool airport. First of all, high elevation. Second of all, loads of terrain nearby. And third of all, the DA is elevated. It's instead of 200 feet, which is standard for an ILS, it's 1,100 feet because of the difficult terrain around it. And this is the lateral profile. Now, we would have to do the calculation for all 3 step altitudes. However, we'll just do it for the 6,500 feet first, and then we'll do it for the ILS decision altitude. So, we're coming into Ohrid, and in this scenario, we're at 8,500 feet, and the outside air temperature is negative 21 degrees Celsius. Runway is 2,300 feet, and we want to first calculate what indicated altitude we need in order to get a true altitude of 6,500 feet. So I could listen to the ATIS and then calculate from the temperature on the ground at 2,300 all the way to 6,500 feet. I could do that. That would be a perfectly reasonable thing to do. Or I could use my current altitude, 8,500 feet, with my current temperature of minus 21 and calculate the difference and do the reverse. If I'm going to descend 2,000 feet, it's going to be hotter by 4 degrees Celsius at 6,500 feet. So around 17 degrees Celsius. Okay, so minus 21 plus 4 is minus 17. So from that, we can then calculate also the ISA. Remember, we need to find ISA dev. 15 minus 6.5 times 2, because we're talking about 6,500 feet. And so at 6,500 feet in ISA conditions, we would get 2 degrees Celsius. The reality is 17. So the ISA deviation is, once again, minus 19. Complete out of coincidence, by the way. Okay, great. So we have an ISA dev of minus 19. So we can then plug it all in into the altitude correction formula. 4 times. Now here's the thing. You see those brackets? It's not a trick question. We are not at sea level, right? So at 6,500 feet, there is not 6,500 feet of air mass between the aircraft and the ground. There's going to be 6,500 minus 2,300 feet, because that's the elevation, right? So minus 2,300 feet. So we find the difference between those two, and then we divide it by 1,000, and then multiply it by ISA dev. So that gives us 4 times 4.2 times minus 19, which gives us approximately, that's a mistake. It should be 319 point, I want to say 0.6. I'm going to calculate that. There's a typo on my part there. It's 319.2, not 0.2.6. It's not an IP address or something like that. It's 319.2 feet. So we round that up to 320. And remember, we add them together normally, right? We add them together for the other way around. However, when we were doing it the other way around, we were trying to find out what our true altitude was, whereas here we want to find out what the indicated altitude is to give us 6,500 feet. So instead of adding, we subtract. So 6,500 minus 320, and we know that 2 minuses is a plus, so we need an indicated height of about 6,820, indicated altitude of 6,820 feet. The great news is we don't need to recalculate ISODEV, right, for the DA. So we've got ISODEV already. So ISODEV minus 19, we get the altitude correction, we plug the numbers in. So I'm using 1100 feet. We could calculate it, so 3357 minus 2284, or we could look at the number inside the round bracket, which says 1073. I rounded up to 1100, 4 times 1100 divided by 1000, times the ISO deviation. That's going to give us 4 times 1.1 times minus 19, which gives us negative 83.5. If we assume that's around 85 feet, we can say that we want to be at 3357 minus 83, or 85, since we've rounded it up. And so we end up with 3442. So our corrected decision altitude is 3442, about 100 feet difference, right? Almost 100 feet, which is quite a significant difference when you're talking about an instrument approach. And that's it. That's a super long video. I hope you enjoyed it. I'm tired, so I'm not going to re-record this. I'm going to leave this as the final recording. If you enjoyed it, please subscribe. Check out ANC Academy if you want one-on-one sessions with myself. I'm Tarek Merface. I'll see you guys next time, and happy flying.